energies in the periodic table. So this will finish up chapter 7. And now ionization energy, your definition is the minimum energy required. So the energy that's required to remove the most loosely bound electron. Now remember, if you're taking an electron from an atom, then you're going to form a positively charged ion. So it's the energy that's required to remove the outermost electron from a neutral gaseous atom. Now, do you remember when we were doing trends in atomic radius and that I asked you to draw lithium, sodium and potassium to draw out the atoms? So you already have those in an A3 sheet. So what I want you to do now, okay, is to pause the video, look at your 3 atoms and consider which of those atoms do you think it would be easier to remove the outermost electron from? So in other words, would it be easier to remove the outermost electron from potassium, or would it be easier for you to remove the outermost electron from lithium? And you need to consider why. So once you've thought about that, then you should be thinking that potassium, because potassium is a bigger atom, the electron is much, much further from the nucleus. So that electron, it would be easier to remove that electron as a result. So the ionization energies are decreasing. Look, they're going from 520 down to 496, down to 419. So the ionization energies decrease as you go down the group. Why do the ionization energies decrease as you go down the group? Because the atoms are getting bigger, the radius is getting bigger. And what else is happening? Well, look at all the electrons that you have in the intervening shells. They are blocking the positive force of the nucleus, trying to hold on to or trying to attract that outermost electron. So the more screening you have in the atom, the easier it is to knock off that electron from the outermost shell. So ionization energies decrease as you go down a group, and why? The atom's getting bigger and there's more screening. So it's easier for potassium to lose an electron than it is for lithium. Okay? Now what about when you're going across the period, across like from lithium to beryllium to boron and so on? Now again, you have your atoms drawn out there going across, so you need to pause the video now and think about what you think. Would it be easier to remove an electron from neon or from lithium? And why? So once you've considered those, now you should be thinking, right, now the atom of neon is smaller. So that outermost electron there is closer to the nucleus than the atom of lithium. So the fact that the atomic radius is decreasing means the outermost electron's closer to the nucleus. The other thing is you've got more protons in a nucleus of neon. So that's a greater positive charge in the nucleus trying to hold on to that outer electron. And there's no increase in shielding because the electrons are going into the same shell. So all of those 3 points there will help you to explain why ionization energies should increase as you go across a period. Now there's 2 exceptions to that, and you need to be able to explain the reason for the exception. So look at beryllium. Beryllium's ionization energy is 900, but boron is 801. That's a drop. We should expect to see an increase. And also nitrogen's ionization energy is 1402 and oxygen's is dropping. So I just want to use the show me board there now to go through that with you. So if we write the electron configuration for beryllium, you can see that beryllium has 4 electrons, so it would be 1s2, 2s2. Boron has 5 electrons, so the configuration would be 1s2, 2s2, 2p1. Now, just bear in mind, you have the ionization energies in your periodic table, in your logbooks, you know, but you just need to be able to explain. So why is there a drop in ionization energy here between beryllium and boron? So the answer is, here, look, you've got a full sub-level here. 2s sub-level is full because you can only put 2 electrons in the 2s sub-level. Okay, so it's more difficult. This is a more stable configuration. It's more difficult to remove an electron from 2s than it is from 2p. The other exception we saw was nitrogen. Nitrogen has 7 electrons, so 2s, and you have 2p3. And oxygen has 8 electrons, so when you write that, 2s4. Now again, we expect ionization energies to increase as you go across the period, but here you can see with nitrogen and oxygen there was a drop that we need to be able to explain, okay? How will we explain the drop? Well, you're going to say that this is a half full 2p sub-level. Be careful with your language now. This is a sub-level, 2p sub-level, 2s sub-level, and that makes the atoms more stable. Therefore, it's more difficult to remove the electron from that. Now, I just want to quickly run back to this next. I'll just finish with that now, 1 second. Now, Oh, sorry. And I just want to show you this now, right? So sometimes in the exam question, you're going to be asked to plot a graph where you have atomic number on the, oh, Lord, what am I doing? So you have atomic number, you have atomic number there on the x-axis down here, okay, and you'd have ionization energies on the y-axis. You might be asked to plot a graph of that, but they'd give you the ionization energy values, obviously. Now, do you see there, we said that going from lithium to neon, we expect to see an increase in ionization energy, and you do, except here and here. So you need to be able to explain why is beryllium's value higher than boron and why is nitrogen's value higher than oxygen. Now you're going to see a similar trend when you look at the third period going across here. Look, you can see this magnesium's ionization energy is much higher than aluminium and phosphorus is much higher than sulfur. Same thing, you look and you see the electron configuration and you'll be able to explain it that way, okay? Now, the other thing then that I just want to run through is evidence for energy levels. How are ionization energy values evidence for energy levels? So if you look here, for instance, this is potassium's one done. Now, potassium has 19 electrons. So if you were to write it out, it'd be 1s2, 2s2, 2p6, okay? Then you'd have 3s2, 3p6, and 4s1, okay? Now look down here. This is where it's starting. It's removing the most loosely bound electron. So the most loosely bound electron there would be this one here, okay? So you're removing that and the energy is low enough. But look what happens from A to B. So what are you trying to do? Once the first electron is gone, look now the situation you're in. You've got a 3p6. Now, how would you articulate that? What would you say? You're going to say that the 3p sub-level, it's not a main energy level because there's no mention of 3D. Okay, it's a sub-level. The third main energy level is not full. There are no electrons in 3D, so you have to call it a sub-level. So the 3p sub-level is full, and that's why it's difficult to remove an electron from that, and you see this jump up here, okay? And then you can see subsequent general rise going along here from B to C, where you're removing the 6 electrons that are in the 3p sub-level. And then look, you see a big jump there again then, look, from C to D. Why? Because you're removing 2 electrons that were in the 3s sub-level. Okay, and then you're going in at D here, then you're going into the 2p sub-level, which is full, look, so you're moving the H there. Then you're seeing an increase again at E, going into the 2s, and then finally you're seeing an increase from F to G going into the 1s. So the fact that you see sudden jumps or rises in ionization energy values is evidence for energy sub-levels. And, you know, because full sub-levels are more stable, you see a big jump when you're going from one sub-level into another full sub-level.